I will present the backscatter communication. I will give some brief history, because this technique actually is not really a novel technique. It exists, but the manner with which we use it, it's new, and it's kind of innovation. I will present also the categories or the families of this technique, because we at least there are, excuse me, so I continue the talk. At least so we know that the maybe a lot of us know the RFID systems, and the RFID systems are actually backscatter communication technique. It belongs to this family. I will give some prototypes that were developed in the literature, and in our lab we are working also on this technique. So my PhD student has already published a paper. She has participated in IEEE conference. So I will give some results of her research. And then finally, I will give some conclusion and some perspectives. Short biography of me, but I think it was already done. I had many experiences in France, Tunisia also. My research fields are IoT applications, sensors for IoT, wireless communication, and antenna. And the targeted application are industry 4.0, e-health. Excuse me, this was not translated, but I can translate it directly from French to English. So industry 4.0, e-health, precision agriculture, etc. I would like also to present my lab. We are in France. The city is called Rouen in French. We pronounce it Rouen, and we are in the northwest of France. We are not very. We are located 130 kilometers from Paris. So this is our campus. This is our lab. These are some views of Rouen, church, etc. And these are two photos for our platform. So we work on characterizing antenna. We have experimental equipment for this. We have an anechoic room, etc. And another team also work on embedded systems, wearable, etc. So these are so we have in our lab 3 teams. I belong to this team. I am a member of this team, electronic and systems team. Our research topics are antenna, EMC, electronics reliability, but we are not limited to these topics. These are the main ones, but we work also on wireless communication, software-defined radio, etc. The 2 other teams work on vision, autonomous vehicle, embedded systems. For intelligent mobility, for this team, computer science, instrumentation, and systems team. And the last one, automation and systems team, they work on fault-tolerant control, diagnosis and prognostic models, methods, etc. We have strong also collaboration with French companies in our region. We have some. We are funded by companies, directly by some companies, and I would like also to be precise. We are a private engineering school in France, an engineering school. They are specific. This is a specific how to say specific. It's different actually from university. We call this in French école d'ingénieur, engineering school. So we have graduate students. Okay, so they will get a degree, 5 years degree at the end of their studies. So now I move to the introduction. So as I said, the IoT technologies emerged last 2 decades. There is an acceleration of the IoT, the connected IoT numbers, especially in industry. And as you know, IoT architecture as a network is relying on sensors at the edge layer. So the main question is how to power sensors. That's the main question. And actually, if we try to continue, if we continue to use batteries, there is a great there are some problems. This alternative has a lot of drawbacks, especially ecological ones. So researchers have already made some choices. They have worked, or from the beginning of the century, from the 2000 yes, they have started to work on what we call energy harvesting. So energy harvesting, its principle, it's very simple. The idea is to convert the ambient energy that could be mechanical, thermal also, and then so we recover this energy and convert it to electrical one. We store it in a capacitor, supercapacitor, and then we use it. So here this could be possible because the sensors should not have a great amount of consumed energy. However, the great drawback of this technique is that it is limited in terms of conversion efficiency. So if you have for example, 1 milliwatts in the input of your sensor as a thermal energy, the output could be only 30% or even less than that, 15%, 30 or 15 or 20. It depends on the domain of the energy, chemical, thermal, mechanical, etc. And this is really a weak, the main weakness point, the main weakness of the energy harvesting. So just to give you some idea about the harvested amount of energy, we cannot exceed the level of 1 milliwatt. And sensors, communicating sensors, they consume much more than that. So the idea there is to change the architecture of the communication block. So we cannot continue with blocks like power amplifier, because they consume a lot of energy. There are some other techniques, but this could not limit the requirement in terms of energy. So in order to explain how this technique is working, I will give an example. You can imagine, so I say here, it's a matter of fuel and cars. You can imagine that you are in this the situation. Your car is broken down, so you have many choices. The first one, you will search fuel from fuel station. This is the classical one. Your neighbor can have enough of fuel and lends you some. You observe a fuel tank with a leak, a few drops, you recover them, and you store this fuel while waiting to find other tanks. Or you leave your car nearby and decide to carpool. This choice is the most ecological one. So this is the idea even for communicating. So there is a perfect analogy between communicating and transport. So analogy between wave, this is what we call a carrier, and the car. So let's analyze this analogy. So the choice one is equivalent to say that we are going to use batteries for sensors. The choice two, it's equivalent to say we are going to transmit wirelessly or to transfer wirelessly the power. This is what we call wireless power transfer technique. And the third one, it's the energy harvesting. You recover energy from other source. You still use your mean of transport, and the mean of transport for the case of the wave is the carrier. And the next one, which is more interesting, is the ambient backscatter communication. So instead to generate your own carrier, you will use another carrier, or what we call an ambient carrier, an ambient RF signal. This is the idea, and this will simplify extremely the architecture, the inner architecture, the circuitry of the sensor. So here the table can give you a good comparison between the situation for the broken car and the information to be transmitted by the sensor. So if we focus on the second table, you can see that for the case of backscatter communication, energy is almost not necessary, and the carrier is external. However, in the conventional architecture of transmitter, RF is generated by the transmitter, so the communicating sensor, and this is very costly. So the idea is no carrier generated by the transmitter, and instead of generating, we reflect incident waves. Okay. So the question, the next question would be, okay, that's interesting, but how we will code binary data? How we will achieve modulation? So there is a nice technique for this, and we will use the same technique that is already used for RFID. So when an incident wave arrives at the level of the antenna, we will make a variation of an impedance. And you know that maybe, I don't know if you know or not, but those who are expert in radio frequency know that by varying impedance, the reflection would be different. When I say this, I mean either the amplitude or the phase would be different when you will make your impedance a variable. And this is the idea. So the first time that this idea was used for the backscatter for communicating, it was in a paper that was published by researchers from University of Washington in 2013. So here I give the details of the architecture of the transmitter. Here you have a stage or some stages for energy harvesting. We will, or the transmitter will harvest energy, but we will divide the necessary amount of energy by 1,000. So from one, instead of harvesting 1 milliwatt, some microwatts would be enough. And this is very interesting. So we will modulate by varying impedance. We will modulate the signal, the incoming signal, and we will reflect it. And here you have in the input the binary signal. Okay. So there are many advantages. No need for powering sensors. Exploits ambient RF signal. No further cost. Suitable choice for IoT application. However, there are many choices for RF signals, and this is still how to say an open question, an open topic research. What type of signal or ambient signal would be the most suitable one for backscatter communications? We can find in literature some tests, some works that have focused on, for example, FM, frequency modulation, radio signals, TV signals, LoRa, 5G, Wi-Fi, etc. So before showing you some results of our PhD students' research, I would like to give or to describe a brief history of this technique. Actually, this technique is not a new one. The idea first comes to a famous scientist or inventor, which is Alexander Graham Bell, who has also invented an apparatus that communicate the audio signals with light by backscattering light. So he is famous because he's considered as the inventor of phone, but he has other inventions. And so this is the timeline. I will not give all details about this, but there are some key dates. So 1880, the discovery of the principle of communication by reflection by Alexander Graham Bell. 1948, a nice paper was published by Stockman, in which he described the principle of communication with the use of reflection generated by mechanical devices. And since 40s, you know, radar was used. He was used first time in the Second World War, and even for civil application, we still to use it until today. In the 16th, development of the RFID prototypes. First application were commercial anti-theft systems, etc. Nowadays, RFID applications are multiple. I can give some example: inventory management, automotive, industry, but also e-health, new applications, not conventional one, e-health, IoT, etc. So the difference, the main difference between RFID and what was proposed in the paper that was published in 2003 is the fact that the signal, the incident signal is an ambient one. If you know RFID signal systems, you know that there is what we call a dedicated reader that will send a signal to the tag, and the tag will respond, will send an answer, will send the identity for the reader. So this is the difference. So this allows me to move to the next slides. Here I summarize. I have summarized the different families of backscatter communication, and RFID systems belong to this one. This family is called monostatic backscatter communication. So there is a dedicated reader or dedicated transmitter, and the transmitter is the same. The transmitter and the reader are the same. So the transmitter have two roles. He is a transmitter, but also a receiver. Actually, it's quite different because we have two antennas and not only one. So this family is called B-static collocated backscatter communication. So backscatter communication is a big family, and there are subfamilies in this big family. And RFID belongs as a technique to this subfamily. So B-static collocated backscatter communication because we have two antennas. This is the reason that for which we have another subfamily. The third one, the C1, we have B-static dislocated communication. This is another subfamily because we have two locations for the antenna. Okay, and the last one is the most complex one, and this is what we call backscatter or ambient base static backscatter communication. So you can imagine you have an ambient source, for example, base transceiver station for mobile communication. You have 5G or 4G signal or even satellite signal from the satellite. This signal will be reflected by the sensor. We call it also tag, by analogy to RFID, and the reflected signal will be received by the receiver. But in the same time, there is a direct path from the BTS. You imagine that there is the original signal, which is 5G, will also receive it by the receiver, and this is how to say, this could be problematic because the receiver could be able to make the difference between the direct path for which there is some information, and the other information for the non-direct path. This information is that of the sensor. So this is what we call a detection and estimation problem at the receiver, and until today it's an open research subject. Okay, so there is another family I try to accelerate. So it's possible also to help tags by wirelessly power them. So instead of harvesting energy, if tag, we can assist, yes, we can assist tag with by using what we call power beacons. This is another technique, another subfamilies. So I will give here some developed prototypes. So this is the article, the paper that was published in 2030. The idea is quite different from RFID, but it's quite similar to a specific family of radar, which is called passive radars. So we are talking about ambient bistatic scenario. You have the title of the paper, and the used incident RF signal was the TV signal. The goal, of course, is to be able to communicate without generating continuous wave. For that, we will use ambient RF signal. There is no longer a dedicated reader, contrarily to the case of RFID systems. However, we should to pay attention because the reflected signal should not be disturbed other conventional communication system like 5G systems, mobile communication systems, LoRa, etc. This is what we call active communication. Okay. So the challenge is to be able to detect and to estimate the transmitted samples at the receiver. So here I explain the idea. The idea is really very simple. I take an example of transmission of two samples that are coded in 1 bit. So if you want to transmit the bit 1, so you will use, for example, this impedance ZL1. If you want to transmit the bit 0 or the 0 bit, you will switch in this position. You will make your switch in this position, and then your reflection coefficient will be different. The amplitude or the phase of your the reflected wave will be different, and the receiver will understand that you have coded your information differently, and the receiver, the bit is no longer 1, is 0, or inversely. So as you can see here, we have just one block. In the case of conventional transmitter, we have power amplifier, we have local oscillator, we have filters, etc. Here we have just modulator, and the modulator is switch, and the switch could be, for example, a transistor. The transistor that will commute between two states. This is a very simple way to implement the modulator. In the literature, there are a lot of applications, especially e-health, agriculture. Unfortunately, I was not able to list all, but there are a lot of applications, e-health, smart agriculture. I will give some, how to say, some images, some photos from papers. For example, here, this work was achieved by Orange Labs, French company. And the idea here is to use smartphones or the signal coming from the smartphones instead of using the RF signals coming from the BTS. So the advantage here is that our smartphones are closer to the tags, and the power of levels will be much higher. As an application, the author of the paper suggests this technique. So he called this asset tracking out of thin air. You can imagine that you will no longer need the infrastructure to track your asset, because if all users agree to use or that your smartphone will be used to detect and track assets, so by exploiting signals coming from their smartphones, we can obtain a reflected signal, and this reflected signal could be exploited in different receiver to know where is the location, where is and what's the identity of the asset. Okay, so you can track your asset everywhere without using code bar, etc. The classical techniques for tracking assets, etc. I have found also other application. Here, yeah, we can be how to say, I have cited this or I have inserted this photo because when you find that possible data rate can reach gigabit, this is very interesting. This is the first point for which I have put this picture. The second one is the use technique that was used to fabricate, to design this prototype. So author have used what we call inkjet based printing using silver nanoparticle inks on flexible liquid crystal polymer substrate. To be honest with you, I am not expert in materials, but when I have read the paper, authors, I have understood that authors have used this process because it's more precise, and we will use a small amount of inkjet of materials compared to other process. So you can see here that even electronics expert needs the knowledge of expert in materials to optimize their systems. Here is a test of a prototype of epidermal sensor, and our PhD student worked on something like that. So this work was achieved by an Italian team and was published in 2020. You can see that there are recent dates. So this is really a hot topic in literature. Finally, a paper published in 2020 by an American team, and here it deals about agriculture precision. It's always the same idea. Using here we use the LoRa signal. We reflect signal in order to have an idea about the humidity, the moisture of in the plants, in the trees also. So now I will give some details about our PhD student work. So we are working on 5G ambient backscatter communication. We have chosen the 5G signal because it was already commercialized by operators, by providers, service providers, and 5G communications have 5G signals have many advantages compared to other systems or communication systems. We have a high throughput, we have a high availability. 5G could enable real-time application. It's being largely deployed. In France, we receive already the 5G signal. In many other countries. However, the limitation is the high path loss because of the value of the frequency. The antenna size also, it's another problem. There are a lot of thermal issues, and there is another issue for the power efficiency and battery life. So this could be an issue if we use conventional communication techniques. However, if we use ambient backscatter communications, some of this limitation could be tackled, especially the thermal one, or the power efficiency and the battery life one, because in battery scatter communication, we use supercapacitor, we don't need a battery. So in the beginning of this work, we have studied the feasible range, and so we have studied the feasibility actually, and so for that we have modeled the system. We have supposed that we have a BTS based transceiver station for transmitting 5G signals. And we have supposed that there is a sensor which is located at a distance of DTS1, and there is also a receiver. So you can see here we have all the geometric parameters. And then we have chosen some typical values, especially for the height of the base station, the height here of the sensor. We have used also standard documents in order to exploit the propagation model. So we have used two propagation models. The first one between the 5G antenna and the sensor antenna. The second one is between the sensor antenna and the receiver antenna. So the first propagation model was a 5G specific propagation model that was published by the European standardization organization, which is ETSI. Okay, so this propagation models was it's recent. I think it was published in 2020, and here we have used the free space propagation model in order to simplify the study and the simulations. So I will show the result of simulation. Actually, of course, there are some other parameters to set up. For example, here the other parameters are the transmitted power, the sensor losses, antenna gain, radiated power at the sensor, noise figure, and we have chosen typical values that we have found in literature or in technical documents. So I will not give all the details of the methodology, but the methodology was really simple. And I would like to say that such work was not done in literature. So this is the first time. This was highlighted by the reviewers. This is the first time that we use propagation model to estimate the range of backscatter communication. Most of previous work focused on the tag architecture, how to say, digital transmission techniques, etc. Okay, so we have used MATLAB, the software, for simulation. We have used what we call PLUMA propagation model for 5G, and free space path loss to model the losses, the power losses between the sensor and the receiver. So I will not give the detail about the equation. So we have used some number of equation for that describe that characterize the path loss in each model. This is the methodology. We insert parameters in the first path loss. Then we have some other equation in which there are relations between different powers. And the goal is to have an estimation about the range. The range for us is the distance. Is the distance between the sensor and the RX, the receiver and antenna. It's not the distance between the BTS and the sensor. This is the range. This one. So as a first step, we have simulated the path loss for the two models. We can see here that there is a little difference. And then, so we have followed the different steps, step by step, each time. So this is a first result. We can see the power level at the sensor. We are still at the sensor. We are still in the sensor level. You can see clearly that if the distance between the base station sensor is not high, so here the distance is given in meters, and if we have not a lot of losses in the sensors, you have a quite high received power at the sensor. Okay, minus 30 dBm. Okay, however, if we have a lot of losses at the sensor and we are far from the base station, we could have we would have a very low received power. So we continue with the same process. We have also used the equation in which we define our signal to noise ratio, because it has an impact, it has an influence on the range. So simulation give a value of what we call sensitivity. Sensitivity for us, radio frequency expert, is the I remind this, is the minimum value of received power at the receiver, for which it's always possible to process the signal and to receive it. So if we have a value that is below this one, the receiver could not process the received signal. And these values are quite acceptable. They are good because they are in good agreement with typical values that we can observe, can find for other communications systems. So minus 94 dBm is good, is a good value. Yeah, so this is the sensitivity at the receiver, at the sensor, excuse me, at the sensor level. So we continue all equations, and here is an intermediate parameter which is called available path loss. Available path loss is the maximum path loss that can tolerate to get the minimum of signal to noise ratio. Okay. Maybe so this yeah, here finally we can show the achievable range, achievable backscatter communication range for a given value of bandwidth. Bandwidth also has an influence on this range, and we have used a logarithmic scale on the x-axis. So you can see that I think if the bandwidth is smaller, I don't remember, but so here we have a logarithmic of that has a value that equals to 3. Just to give you an idea, we cannot have a range that exceed to 100 meters or 200 meters. With however, this range is achieved with a value of a gain that equals 0. So this is another interesting parameter that can use it to improve the range, to increase it. So here we have plotted in 3D the backscatter com range as a function of sensor losses, distance between the base station and the sensor, and the total antenna gain. When I say total antenna gain, is this means the gain of the sensor and the gain of the receiver, sensor and Rx. And here I think we have a logarithmic scale also. Okay, so if here you can see that this region is especially interesting. It's in it's not in dark color. So we have a value of logarithmic of the range that almost equals 0, and this could be achievable if the distance, if the sensor is close to the base station, and if we have also a few of sensor losses and a grid value of the gain almost 40 dBA, the sum of the two gains. So we summarized all this in this table. So you can see, for example, if we have no gain, we have a very weak value of range, almost 10 centimeters. However, if you have 40 dBi, the sum of the two gains, you multiply this by 100. So this is interesting. And here we have considered 20 dB as sensor losses. So ideally you should find a way to reduce your sensor losses. Finally, I move to the conclusion. So as a conclusion, ambient backscatter communication, and especially 5G, beyond 5G, 6G ambient backscatter communication is a promising technique for a minimum cost and low energy transmission. It's a suitable technique for IoT application. I have given a brief history of this technique. And I have given also some examples of developed prototypes in literature. We have started to work on this technique in our lab. our PhD student has simulated the feasible ranges in the case of 5G ambient backscatter communications. Results are quite good, are quite acceptable, because with a minimum of losses, we have now we can say we have no longer doubt that such system, such communication is feasible. We can reach 100 or even 200 meters of transmission. There are still many challenges for the architecture, especially when you have many sensors that communicate with one reader. This is what we call, this is a very known problem in communications, in wireless communication, and we call this a multiple access problem. So we are not working on this, but in the literature is really very, there are a lot of works, lot of researchers work on this. We are focusing on hardware problems. We are trying to optimize the architecture of the tag in order to optimize its consumption and to optimize especially the range. But also we are thinking about how to optimize the data rate. There is also this technique is sensitive to the environment. We target the specific, our PhD students' work target a specific use case, which is the what we call epidermal sensor. Epidermal sensor that will be set up on the skin, and the skin could disturb the communication because the impedance would be variable. So this is a complex problem, and we are trying to find a way to tackle, to address such issues. Regarding the materials, yes, as I said before, we are not expert of materials, but we are thinking, we think we can use innovative, novel materials for substrates. Flexible electronics are largely used in or were largely used by researchers that have worked on these topics and have developed fabricated prototypes, especially inkjet printing manufacturing. This is a precise process. Some researchers also use what we call metamaterials in order to design performant antenna with nice gain, antenna that are directive or not. It depends the use case, etc. Last point, yeah, there is also another interesting research topic, excuse me. This is what we call connected material. You can imagine that material will be smart and could communicate without circuitry. This could be possible thanks to backscatter communication. Actually, some materials could change its impedance when they are exposed to RF signals. And this is good because thanks to that, we can achieve a backscatter communication. This is not possible with conventional communication. However, with a minimum circuitry that is needed in backscatter communication, we can really conceive and fabricate what we call smart materials and wireless robotic materials, for example, with just materials, without circuitry, without electronics. So this is also an interesting topic. We are not working on that, but I have found this in literature. So at the end of this presentation, I give some references. The most of them are recent. They were published in the 2 or the 3 last years. So thank you for your attention. And if you have any question, please don't hesitate. Thank you. However, I no longer heard you.
Thank you, Professor Bakar. Any questions? Does anybody have a question in the audience for Professor Bakar? Okay, I guess he was very, very elucidative and illustrative in his talk, no doubts. Thank you, sir. Thank you for joining us and taking time out and addressing the conference today. Thank you.
Thank you.
We would now be moving on into the final session for the conference, the valedictory function. Please just give me 2 minutes. It has been an absolute pleasure and honor to have you all here. And I, on behalf of the whole MAM23 team, would like to thank you. A heartfelt gratitude for all of you. It's not a matter of joke to take time out 3 days in a row consecutively and to sit here. Just sitting here and listening in itself is very arduous. So thank you once again. And we hope to see you every year, and try and make things as rigorous and yet more communicable and more amiable. And on that note, I would now like to request Professor Atul Thakur sir, Director AINT and ASAS, Amity University, Haryana, to please commence the function with the report on the 3 days of the conference. Sir, please.
Very good afternoon. So I'm going to start with the day 1. So day 1 of the National Conference on Multifunctional Advanced Material began with invoking blessings from Goddess Saraswati with lighting of lamp, with welcoming the guests. The chairman of the conference appraised about the theme, scope, and diversity of conference. In this address, Professor Madhukar, Pro Vice Chancellor, he discussed about the importance and varied applications of advanced materials. So no doubt he's a person from the management, but he nicely spoke about the concepts of materials. Then Honorable Vice Chancellor, Professor P.V. Sharma, in his visionary address, highlighted about the importance of nanoscience and nanotechnology. As you know, he always talks about nanoscience and nanotechnology, and he says nanoscience is the science of God. And the chief guest of the day, Professor Pratik Kishore, Director TVRL Chandigarh, advised the use of advanced material in the defense arena. Therefore, the conference proceeding booklet was inaugurated by the dignitary. The technical session 1 began with the plenary talk by the Professor Pratik Kishore, Director TVRL, who highlighted about the development of advanced materials and their importance in different defense applications. Then the keynote address was delivered by Dr. Mrinal Pal, Chief Scientist, Head Functional Material and Device Division, CSIR, Kolkata. So he talked about the health monitoring system by using semiconductor nanostructure-based gas sensors. So he basically discussed a variety of sensors, like I think about 22 types of sensors he has discussed in his speech. Then the technical session 2 started with the invited talk of Professor Basant Singh Sikarwar from Amity University, Uttar Pradesh. So he talked about the development of super hydrophobic surfaces using nanocore shell structures. Thereafter, another invited talk by Professor J.C. Kunyal, scientist G and head, Center of Environment Assessment and Climate Change, G.V. Pant Institute, Almora, Uttarakhand. He talked about the climate change in the Western Indian Himalayan region by the aerosols. The talk covered different aerosols, the effect on environment. So the talk was quite enriching. Thereafter, poster presentation was held where the participant that included students and researchers, they put their posters and they were evaluated by a panel of judges. In the next session, oral presentations were given by the young researchers. And even the students of masters and bachelor students, I was quite fascinated by one of the talk of our student BSc fourth semester. Probably she's going to get something. So oral posters were made by, oral presentations were made by Miss Nancy, Kashmas, Shilpa, Taneja, Amitendra Singh, Saurabh, Anjali, Kishore, Anand, Neetu, Manish, and Sarthak. So that concluded the day one. And then on day two, it started with the first technical session by Dr. Sanjeev Verma, scientist E, TVRL Chandigarh, who talked about the non-Newtonian fluids and their application in personal and protective systems. Then the second invited talk was from Professor Pankaj Thakur from JNU, Special Center for Nanoscience and Nanotechnology. He spoke about the morphological control of nanomaterial by simple methods. So talk was quite informative. So he used very simple method and technique to explain how nanoparticles are made and their practical applications. Then third talk, invited talk was made by Dr. Ashish Seni, scientist F, TVRL. So he talked about the advanced materials, their applications and the challenges. Then we started thereafter technical session 2. The talk was made by Dr. Plash Kumar from Cosmoferrites. So Cosmoferrite is a industry based upon magnesium ferrites for multiple applications. They make transformer, core shell, filter. So he talked about the different parameters, aspects, devices, different geometries, how do they make, whatever furnace they use. So it was quite an enriching talk. Then the next speaker was Professor David Wang from Taiwan. So he talked about the preventing the development of urological chronic pelvic pain syndrome. He discussed the various experiments to establish the efficacy of what is that? I cannot read properly. Nanoparticles in cancerous cells. Can you please switch off those lights? Then technical session 4 started with the talk by Dr. Yassin. Dr. Yassin is one of the top researcher in the Saudi Arabia. He is, top 2% scientist by, thank you. He's top 2% scientist by Stanford University ranking, and he talked about the different methods for enhancing the performance of high temperature superconductors. So, we have seen the minute explanation how superconductors are made in his lab, and he's using liquid nitrogen to make levitation. So he emphasized about the future of the superconductor material in different devices, including electrical vehicles. So next talk was made by, again, yet another great scientist, researcher, Dr. Nikhil Bhalla from University of Ulster. So he's working on different types of biosensors by using nanotechnology. So he explained about the nanoplasmonic biosensor for various for virus detection. Thereafter, the next session was on oral presentation, and that was end of day 2. Day 3 was started with the talk from Fai Wang. He's the dean in University of Information Science and Technology in Nanjing, China. So he nicely explained like how integrated circuit they're used and they're made, how we are doing the electromagnetic shielding, electromagnetic capabilities, testing methods, different techniques, instruments. He explained each and everything. Thereafter, another talk was made by Dr. Vivas from Taiwan. So he elaborated on thermal management of flexible electronics through microfluid, molecular heat sinks, and intricate channel design, and improve the material characteristics. So Dr. Vivas is expert in refrigeration system, welding management, and he's recently using nanotechnology in all these domains. So he's also supervising two of our students who are doing internship under T program in Taiwan for 6 months. So thereafter, the next speaker was Professor Arun Kumar, Vice Principal from the Chetinan Academy of Education and Research, Chennai. His talk was based on the local drug delivery, hypothermia, and the different medical devices, use of nanotechnology. So the talk was also quite informative. Then Professor R. Nagarajan from the Department of Chemistry, Delhi University, discussed about the fascinating properties of materials. He was very genuine person. He was very honest. He explained each and everything quite nicely, and maybe all of you got benefited from the talk. Then thereafter, Dr. Deepshikha Rathore, she's working on different types of ferrite materials. I've seen like she's working on printing electrodes. I personally visited her lab. She's doing a wonderful job. That's why I thought to invite her to present her work. And she spoke wonderfully on the nanoferrites and their importance, their structure, their composition, various type of applications, and specifically for the gas sensor applications. And thereafter, Pravindra sir, a former director at SPIC Lab, DRDO, presently working at PVL, he explained in his valedictory address on the global technology leader, key enabler in process of sustainable development and innovation. And finally, there was one talk left from one of the scientists from France. He's working in Silec, Rouen, close to Paris, Professor Sabi. So he spoke on backscatter communication from the idea of first prototype manufacturing. So he's working on different types of antennas, specifically on patch antenna. And again, he's working on 5G technology. So he's publishing so many articles. He's collaborator with us on characterization of our samples. So the talk was also wonderful. So overall, we had 25 plenary or invited talks and 3 poster sessions, and 5 sessions for oral presentations. And I hope all of you have enjoyed all the sessions, and some of the participants will get best awards for the poster presentation, for best award for the oral presentations after this report. So from this dais, I would like to thank our founder president, sir, our chancellor, Dr. Asim K. Chauhan, our vice chancellor, Professor P.V. Sharma, our pro vice chancellor, Professor Madhukar, and all the administrative support which we received from the admin department, ESCO, our photographer, Srinivas, who is always here, the first person to enter the hall. And who else? I'm sorry if I'm left, huh? All the faculties, yes, of course, all the faculties of ASAS and AINT, all the students, participants, everyone. So now we are going to start with the award ceremony. Okay. So I would like to request Pravindra sir to bless us with the the visionary ideas which you had with your vast experience. Blessings, sir. Thank you.
Good afternoon once again. And I'm really thankful to Professor Atul Thakur and the organizing team, Dr. Prateek Thakur, Pro Vice Chancellor, and Vice Chancellor of this university, for giving me an opportunity to come over here and discuss the things with you. It's always a pleasure to be with young people. It's always a pleasure because they are the future of the country. The detailed report has been given by Professor Thakur. It was really a very, very vast, areas which were covered during this seminar, from drug delivery to nanomaterials to electronics and whatnot, mechanics and everything. So almost the total spectrum of materials was covered in MAM 2023. And as she has said that we want you every year. So I hope and I wish that every year you organize this kind of a conference in which people from diverse disciplines, they come together and share their knowledge. It is basically a platform in which once area of work, it gets communicated to the others, and others also get inspired, maybe to, if they find appealing, to work into that particular area. That's how the knowledge grows. And when I say I have worked on many projects, basically knowledge and information, it can come from any quarter. So no idea is a good idea or no idea is a bad idea. So idea is the idea. Only thing is that if you work sincerely on that particular idea, it may get realized in times to come. I'll tell you one my own story. Say when I joined PBRL at Chandigarh, that is the DRDO's premier lab in ballistics and armament systems. I joined, I was a mechanical engineer. I did not know what the explosive is, what explosive systems are, and what things are. But at that point of time, I had one small dream that, I'll work into areas which can help, our forces. Because, I was an NCC student also during my, student days. And that time we used to get a rifle, which was 303 rifle, and which used to weigh about 7 kgs, 7 to 8 kgs, very heavy. Or during that training, NCC training, they used to ask us to fire. And when we used to fire that rifle, shoulder mein uska bahut, recoil used to be very heavy. Then there were other things which we were discussing, we were thinking. But when I joined PBRL, so I thought, yeah, it's a very good place where we can, work upon all these systems. So PBRL was a test and evaluation laboratory only. That time we used to get, the ammunitions from outside, maybe from Russia or maybe from Israel or from some other countries, and just test and evaluate it. And then say that, yes, this is okay, this is not okay. So that kind of a situation was there in early 80s, 89 or 88, that time of that point of time. Then, somehow we got the idea that we should work upon some systems which can, improve upon. So I gave the idea that we should develop a grenade, this thing, the multi-mode grenade, which I have shown you. Nobody was a taker at that point of time. It took, years together to convince people, yes, we can make this kind of a system. So it is basically the pursuance which paid us. And that idea finally got materialized. It took more than 10 to 15 years, if I'll say that, if I start from day one. But today it is one of the good products which is there with Indian Army. Indian industry is producing it and exporting it. And as I told, it is more than, 600 crores per year. That is the value of that particular product. So it gives a lot of sense of pride and sense of, that we have done something. So basically work upon an idea. You all are young people, you may have some idea, and consistently be behind that idea. That is my message to you all, and try to, improve upon the existing systems. Today, something may be there which you feel that it is good enough, but there is always a scope of improvement. So do that improvement. This will benefit the society, this will benefit the country, and this will give you a lot of sense of pride. So with these words, I once again congratulate the team, organizing team, as well as I thank all the organizers for giving me an opportunity and share this dais with you all. Thank you. Thank you very much. Achha.
I would also like to request Anupama Thakur ma'am, Professor Anupama Thakur ma'am, to please come on the stage. Please do give us the chance to honor you. Nothing major. Preeti ma'am. We would like to begin with presenting a memento to Pravendra sir. I would like to request Professor Preeti Thakur and Professor Atul Thakur to please present the memento. We would also like to take this opportunity to thank Professor Anupama Thakur ma'am, and a small token of gratitude. I would like you all to please stay on the stage and just take 1 more minute. We would also like to now felicitate our keynote speakers. I would like to request Shri Pravendra Kumar sir, Anupama ma'am, Professor Preeti Thakur ma'am, and Professor Atul Thakur sir to please hand over the certificates. First, I'd like to request Dr. Deepshika Rathore to please come on the stage. So, next, I'd like to request Dr. Kalia to please come on the stage. Dr. Rahul Kalia. I would like to request all the HOIs, Sia Pathak ma'am and Chandra Molly sir to please come on the stage, and Ambika ma'am. Please do join us on the stage so that we can proceed with the we would now be proceeding with the Srinivas ji, please ये projector वाला light off कर दीजिए. Thank you. Okay, now we would be beginning with the distribution for the best poster and oral presentation awards. I will start with the oral presentation. The first award goes to, it is shared by two. There's Mr. Amitendra Singh from Amity University, Haryana, and Dr. Ankur Chauhan, Chettinad Academy of Education and Research. First, I'd like to request Mr. Amitendra Singh to please come on the stage. We would like to request Shri Pravendra Kumar sir and Professor Anupama Thakur ma'am to kindly do the honors. Next, the first prize for oral presentation is Dr. Ankur Chauhan, Chettinad Academy. So he's not here with us. Then the second award goes to Miss Anjani Jain, AUH, and it's also shared with Mr. Savat Shivalkar, IIT Allahabad. We have Miss Anjani Jain on stage. The third prize goes to Dr. Shilpa Taneja, GBGS Memorial College, Sona, and Miss Trishala, MMU. We have Dr. Shilpa Taneja on the stage with us. Now moving on to the posters. The first award goes to Shipra Varshney, IP University, and Yaksha Varma, Shulini University. We have Shipra Varshney, IP University on the stage. The second award goes to Deepak Sharma, Central University, Himachal Pradesh. I guess, so okay, he's there, Deepak Sharma. Okay. The third award for the poster is once again shared. We have too many able students. Shared between Gunjan Grover, Punjab University, Chandigarh. Gunjan Grover, okay. We would like to request Professor Anupama Thakur ma'am to accept it. Thank you. And the next one is Kundan Asset AUH. Do we have Kundan here? No. All right. With that, we come to the close of the award ceremony. I'd like to thank everybody. Thank you. Thank you, sir. Thank you. We would now be moving on to distributing the certificates for participation. May I please request Professor Atul Thakur sir to please come on the stage. We begin with the certificate distribution. Anu Singh. Anu Singh. Muskan Jain. Inshallah. Jao, go. Shivani. From behind. पीछे से जाओ. Shivani. Go. Latika. Sangeeta. Indraveer. Reena. Mahek. Muskan.
As your name is being called,
And you want to.
श्रीनिवास जी लाइट जला दीजिए स्टेज की.
I would like to request you all to be a little more attentive and nimble on your feet. Kirti Sharma. Do we have Kirti Sharma here? Utkarsh Kharkwal. Kundan. Aniket. Pranav. Ayush. Ujjwal. Manan. Namita. Deepika. Do you have Amit in the audience? Amit Prajapati? Jayesh Kumar? Manoj? Jyoti? Manoj. Jyoti. Meenu. Nancy. Meenu. Meenu. वहां जाइए, वहां पे आ जाओ. Meenu. Nancy is not here. Priya. Jyoti Yadav. Rajni. Aanchal. Rekha Rani. Durga. And you are? Garima. Aarti. Yadav. Abhilasha Sharma. Geetika. Nisha. Kumari Suchitra. Akshita. Amandeep. You are? Kumari Suchitra. Akshita. Isha Gupta. Muskan Batra. Pinky Yadav. Gunjan. Pooja, Sapna, Deepika, Rahul, Akash, Ranzant, absent. Okay, she's here. Poonam, Deepak Sharma, Renuka, Deepak Sharma. Yeah. Renuka, okay. Komal, Prabha, Dhananjay, Shipra Vashne, you are Dhananjay, Ankit Rao, Ripun Yadav, Naresh Sharma, Raksha Rathor, Nancy Dawal, Nancy. Go, you should take a photo with sir. Wait 1 second. No, बहुत पहले आया था. Shipra. Nancy, do we have Nancy Dawal here? No. Sudha Yadav. Sudha. Shilpa Taneja. Amitendra Singh. Amitendra is there. Amitendra. Anjani Singh. Saurabh. Kishore, Ajay Kumar. Anand Salvi. Acha. Manish Nagar. Neetu Dhanda. Sarthak. Pratipati Naga. I'm hoping I haven't missed out on any names. All right, thank you. If you have missed out, in case you haven't gotten the certificate, you can contact Dr. Lucky Krishna, IMIT Center for Nanotechnology. Now, I would like to request Professor Preeti Thakur ma'am to please give her vote of thanks.
Good evening, one and all. I would like to thank on this concluding day of National Conference on Multifunctional Advanced Material. I would like to thank our guest today, Shri Pravindra Kumar, ex-director SPIC Lab DRDO, and Dr. Anupama for gracing the occasion. I would also like to thank all the other invited speakers who had taken their valuable time and given the valuable talk here. Thank you all. I would like to thank Amity University Haryana for specifically giving us this platform, and our IT department and or the other hospitality team, everyone, other administrative department. Next, the organizing team of MAM 2023. I think they deserve a big round of applause. All the faculty members, students who were part of this conference, who work day in and day out to make this conference successful. And I hope all of you liked all the sessions, specifically the invited talks from our very own speakers from India and from abroad, and also the oral and poster presentations given by the young researchers, students, even the MSc and your bachelor students, they were a part of this. So I hope all of you enjoyed a lot. and had a successful deliberation and days of collaboration, and you had contact with so many different speakers who were here. So thank you all very much. Thank you to our Vice Chancellor, Honorable Professor P.B. Sharma ji, our Pro Vice Chancellor, for always encouraging and supporting us. Thank you all. And thank you all the students, even those who had just participated. A big thank you to all.
Thank you, ma'am. I would now, what do I say? It has come to an end. Okay. When it started, I thought 3 din kab pure honge, jaldi hi pure ho gaye. It's a mixed feeling, honestly. I'll be very, very honest. But thank you once again. Preeti ma'am has already done the needful, but I guess we can never thank you all enough. And with this, see you next year. The pressure is on Professor Atul Thakur, sir. No pressure on us. And with this, I would like to request everyone to please, proceed right outside the D block or D block. Do you all know where D block is? I guess you're all internal members here. The ones who aren't, you can follow us. D block, right outside D block for a group photograph. Please, all of you, please join us. Thank you. Please, 1 second, a little flap. Preeti ma'am, Professor Preeti Thakur, please come on stage. We have to honor ma'am. And I would like to request Professor Pravendra Kumar sir, Professor Anupama Thakur ma'am, and Professor Atul Thakur sir to please come on the stage and honor Professor Preeti Thakur for her endless and unwavering work to make this conference a success. Sir, please. A heartfelt thank you to the convener of the conference. We would also like to request Ritesh sir and Abhilash sir to come on the stage. I think they can run a marathon after this. We all should know the real faces or the muscle or the legs which worked behind this conference. Absolutely. A huge round of applause for Ritesh sir and Abhilash sir. Thank you. I think now we are done. Sorry for the flap. We'll move on for the group photograph now. And thank you to all the students. But then students काम करते हैं.